Good morning, everyone. Happy Wednesday. So far in this course, we've been focusing on uncertainty around loads and resistance. So we talked a little bit about structural steel the first day, how we can calculate what we expect the resistance to be, but there'll be some variability around it. We talked about how structures work, and so we looked at gravity framing, concepts of tributary areas and widths for joists, girders, and columns. And for the last few days, we've been talking about gravity loads. So we did dead and live loads, snow loads, and one of the key aspects of how we treat those loads is, for the most part, we assume that they act more or less uniformly over the floor area, right? That makes the math for us very simple. It's not exactly right, but it's adequate for the purposes of performing the structural analysis we need to perform, and eventually to select some members to resist those forces. In lecture 3, we talked a little bit about, lecture 4, we talked a little bit about braced frames and bracing in structures and how lateral forces might act on a structure. Basically, we saw for a uniform pressure that might represent wind, we saw that we could treat the floors or the wall system that the wind is acting on as if it was sort of a floor system. We treated the floors as if they were joists and the brace frames more or less as if they were girders. Used the tributary width approach, some statics for a simple beam to get actions on our braced frames. The types of lateral loads that tend to act on structures, as you identified in lecture 4, were primarily wind and earthquake loads. And so for the next 2 days, we're going to be talking about the wind and earthquake loads that are difficult for us to assess, but we still need to be able to do that. Okay, so today we're going to be talking about wind loads. Again, this is the next section of Division B, Part 4. So this is section 4.1.7. You'll find it right after snow loads. Again, presenting the highlights, but you're really going to need to go and actually read 4.1.7. There's a whole lot of stuff in there. You might notice if you read the sections, dead loads, short, live loads, bit longer, snow loads, bit longer, wind loads a bit longer, earthquake loads really long. Okay, so as you go through these sections, we're kind of going through more complicated loading scenarios. So we're going to spend one complete lecture talking about wind loads today and one complete lecture talking about earthquake loads on Friday. The interesting thing about wind and even earthquake loads is that they're not really static forces. And unfortunately, we've been conditioning you in civil engineering courses to always consider the equations of static equilibrium. Some of the forces is equal to 0, which means there's no net acceleration. Unfortunately, for wind and earthquake loads, there can be significant movements of our structures, significant accelerations, and that can cause things to be a little bit difficult. If we think about some aspects, the simplest part is how the wind acts on the face of a structure. Okay, we've got a wind coming in from one side. Some terms, the face that the wind is blowing toward is called the windward face, and the opposite side is going to be called the leeward face. Okay, so we're going to be talking about windward pressures on buildings and leeward pressures on buildings. Windward pressures are straightforward. Leeward pressures are very complicated, but we're going to simplify things as much as we can so that we can more or less treat it as a statics problem. Those of you who took fluid mechanics may be familiar with some of these equations here. We basically have what would be another form of Bernoulli's equation. We've got some kind of static pressure, and we've got some kind of wind velocity. Okay, so where the wind is just sort of blowing along, there's no net pressure in that wind stream, but there is a velocity, right? The air is moving with a certain velocity v for the free field coming up towards the structure. And when the velocity starts to hit the building, it has to go from whatever the velocity is down to essentially 0, right? The air is blowing towards the wind, it hits the building, it stops. That area is called the stagnation point. It's where we've got 0 velocity. And so basically we can take the velocity that was upstream and say, well, now the velocity is 0, but there's a pressure that has to be the result of that velocity coming down to 0. Okay, so here where v is 0, we basically have a pressure on the windward face that's essentially equal to whatever half the rho v squared term was for the free stream of air flowing towards that structure. Now, that's simple because we're basically going to say, okay, we've got a velocity of wind that's hitting the structure. The pressure is proportional to whatever the velocity is squared. Okay, so we'll talk about measuring wind velocities and how we can figure out what those might be. Now we've got a little friend with us here. That's a lot of fun. A little bumblebee trying to figure out where it needs to go. Might be a wasp even. We'll leave it there. Might be distracting for us. What happens on the other sides of the structure is very complicated. Okay, let's see what this guy actually is. Yeah, he's just a little honeybee, so we'll try and get him to get out of here. Come on, bee. There he goes. Anyway, the stuff that goes on the other sides of the structure are quite complicated. Basically, because there's a blockage here, we're preventing the flow of the air across the complete volume of space that the wind is blowing toward. So as the wind tries to go around the structure, the area of flow is reduced, and so the velocity increases, right? That's a concept you learn in fluid mechanics. The velocity increases, so it's quite high, and the velocity of air inside the structure is technically zero, right? So when you have velocity on one side of fluid flow and zero velocity on the other side, you end up getting a net outward pull, right? So the pressure is actually pulling on the walls away from the structure. And then as it goes around the structure, this is what's called the bluff body. And this is advanced fluid mechanics that I'm not even super familiar with, but the idea of having a rectangle in the way of fluid flow, they refer to that as a bluff body. It has friction, it creates turbulence, and basically as the wind flows around, it starts to become more turbulent, and we start to shed what's called vortices. We basically have many areas of high turbulence, similar to like how a wind would spin in a tornado, and so these are called vortices, and so this is called the wake region. When we have turbulent flow, Bernoulli's equation is no longer valid. Okay, basically what happens to the structure more or less, as it gets taller, as the wind blows at it, the wind's going to push the structure, but these vortices are also going to cause it to twist and sometimes move side to side, and this can be a very complicated problem. If we're dealing with structures that are short and stiff enough, we can more or less treat these kinds of pressures and fluid flows acting on our structure as an equivalent static uniform pressure. And we looked at this picture in lecture 4 sometime last week. Basically, on the windward face, we're going to more or less assume that the pressure is uniform. On the leeward face, we're going to assume that there's a uniform negative pressure or suction on the back face. That's not shown here, but we're basically going to assume that in this wake region that we can adequately treat that as if it's a uniform suction along the back face. And we are going to get suction on the walls that are parallel to the flow of wind. That might be important for the design of the cladding system or other structural elements that are trying to keep the walls in. But in terms of the total net action of the wind acting on the structure in one direction, it's really going to be the windward pressure, and the leeward pressure that are going to be important to us for the calculation of the lateral forces acting on our brace frame. Okay, so we went through calculating the forces on the brace frame for a problem that looks something like this. Now we just have another uniform pressure on the other face of the structure. Now we have to talk about what those pressures are going to be and how we calculate them. Okay, so basically after this, you should be able to determine first whether the static procedure that we're going to be talking about today is applicable and something that you can use for the wind load calculations for your building. Sometimes you won't be able to use the static procedure, and we'll talk about when that might be. You should be able to define, describe, and quantify the factors used to calculate the specified wind load pressures using the static procedure. And kind of the real crown thing here is you have to be able to calculate the specified wind pressure acting on your regular building using the static procedure, accounting for some partial loading and torsional effects as required. Okay, does anyone have any questions about what these things mean in terms of what you should be able to do after the lecture material this morning? Okay, so again, wind loads, next section here, 4.1.7. It's a longer section to read, but you need to go read it. I'm going to present the highlights here, but okay, that's fun. Retry. But before we get into this, we're supposed to have a poll everywhere question here that is now working. Thank you. So basically, it's very similar to the snow loads question that I asked the other day. What do you expect would influence the actual pressure of wind that we're going to design our structures for? I'm going to go and just make sure that it's actually active here because I noticed the timer is not counting down. Gives you a couple seconds to think about it. What things would influence that uniform pressure that we might design our structures to resist? It is locked, so give me a second here. Oh, come on, get it here. Of course, this is in the way. There we go. So what kinds of things do you think will influence the pressure we have to design our structures for? Building height, perhaps wind direction, climate and location, of course, being important. Their surface area. Location, of course, just like snow loads, is going to be important. The wind tends to blow different velocities in different regions, depending on how close you are to oceans and inland. It's also going to depend on topography. That's a great word, right? So if you're higher up a mountain, winds are going to tend to be faster. If you're lower in and surrounded by hills or structures, you're going to have lower wind speeds. Wind speed, of course, is going to be quite important here because we just talked about it. The wind speed or the pressure that a building has to resist is generally proportional to the wind speed or velocity squared. And the height of the structure, some of these things, so area, surface area, height, those tend to come into what I would call the aerodynamics of the structure, right? The wind blows by, depending on how aerodynamic your structure is, it's going to have higher or lower pressure. It's like a fancy car, right? If you're driving a school bus, it's not going to be very aerodynamic, right? So you can't go that fast before you get a lot of vibration and the gas mileage goes down. But if you're driving a Lamborghini, it can go quite fast without any kind of wind interference. And so aerodynamics of our structures are going to be important. Those are fantastic words. Thank you for that. The first thing we need to do is determine what procedure we need to follow to calculate the wind loads. This is boring, but basically all it says is we have to determine what the wind loads on a structure are going to be using either the static procedure, a dynamic procedure, or a wind tunnel procedure. Okay, so simple structures that are short, and basically what we have here is it says for buildings that are not dynamically sensitive. That's a loaded term, and I'll show you what that means here in a second, but if it's not dynamically sensitive, we can use the static procedure. So basically, the first thing in our brains we should be asking for this course is our structure not dynamically sensitive? And if it is, we can proceed. If it's dynamically sensitive, we use the dynamic procedure. If it's very, very dynamically sensitive, we can't use any methods of calculation. We have to send this off to a wind tunnel specialist. They're going to build a model of the structure. They're going to blow wind at it and see what that looks like. So we've got this term dynamically sensitive, and that's a little bit difficult to figure out. What does dynamically sensitive mean? Well, basically, there are a couple things that go into whether or not a structure is going to be dynamically sensitive. One of the things is the height of the structure going to be less than 6 times the effective width? And so for short, wide structures, they tend to not be very dynamically sensitive. And so these are the widths here, widths at each level, width of building at each level. And so for a regular structure, like your building project, design project, if the floor is the same height or the same width at every level, then W is just the width of the building. Okay, this is just a way to weight average the widths of the structure at different levels. Sometimes buildings can go in and out like that. If the height of our structure is less than 6 times the width of the structure, the effective width, then it is HN is less than 6 times the width. So if it's not less than 6 times the width, we need to tend to go towards a wind tunnel procedure. But if it is, the next thing we need to check is the fundamental frequency of the structure. Everyone here, I'm assuming, has done some kind of wave physics, right? In high school, did you like take the spring and snap it and watch the wave go back and forth and count how long it takes to come back and forth? Buildings also have a natural or fundamental frequency that they want to vibrate with. So I've got these 2 Molekit models here to demonstrate that concept a little bit. If you're watching the video, you're not going to see it, and that's a shame. But basically, short structures, I'll try and move my laptop out of the way here so that everyone can see it. But short structures, if I was to take the structure and let it vibrate back and forth, it vibrates quite quickly, right? Several times per second. And I was trying to measure it earlier today. This little guy here vibrates 1 complete cycle. So a complete cycle is from start to finish, about 5 times in 1 second. Okay, and what that means is that the fundamental frequency, right, for the short building here is 5 hertz. So in this case, for a little short structure, our fundamental frequency is more than 0.25 hertz. 0.25 hertz is really long. That means it takes 4 seconds for a structure to vibrate back and forth once. So really flexible, really tall. So our little structure here would be not very dynamically sensitive. Okay, so this first part here, if Hn is less than 6W and Fn is greater than 0.25 hertz, it's at least not very dynamically sensitive. The next box is the height less than 60 meters? And if it is the height less than 4 times the effective width? And if it is, are we looking at a new fundamental frequency here being greater than or equal to 1 hertz? Okay, so I've got a taller structure here. I'm going to do my best to try and pull it to vibrate back and forth. And I was trying to measure the frequency earlier today. If you were to count, for example, I might say 5 cycles. So I might pull it to here. 1, 2, 3, 4, 5. It's about 1 hertz. It's about 5 cycles in 5 seconds. And so in this case, for the taller structure, our fundamental frequency is 1 hertz. Okay. So in our case here, for this this taller structure here, we're kind of right on the line of this. It's probably like 1.1 or 1.2 if I was to really figure it out. Even that structure that takes longer to vibrate back and forth, its fundamental frequency is still short enough that it's not going to get blown around in the wind too much. And so in that case, it's not dynamically sensitive. And because it's not dynamically sensitive, I can use the static procedure. It's very difficult to figure out what the fundamental frequency of a structure is, but there's a very simple equation here that you can use for a height in meters. The fundamental frequency tends to be about 22 divided by the height in meters, and that's an estimate. It's going to be a lot of variation around that, but that's something that you can use to estimate whether or not your building is going to be very dynamically sensitive, or not dynamically sensitive. Okay, so we need this, and we need the overall height of our structure. And with those 3 properties, we can go through this flow chart and determine what it is we need to do. If it's very dynamically sensitive, you're going to need to do a wind tunnel procedure. And there's a somewhat internationally famous company in Guelph, RWDI. They're a wind tunnel and wind engineering specialist firm. And this was the 3D model that they used to do the wind tunnel testing. They actually did the wind tunnel testing for the Burj Khalifa in Dubai, which is pretty cool, right? So they built this 3D model, 3D printed it or did whatever. They instrument it with a bunch of pressure gauges. And then in wind tunnel, they literally just blow wind at it as fast as they possibly can. Okay, or not as fast as they can, but to match what you expect the wind speeds to be at that site. You can tell a lot of effort goes into this because they're even modeling the city or the other structures around it. And so that's a pretty complicated procedure. At the same time, it's very accurate. It's pretty, I would say, compared to more advanced simulations, it tends to be an easier process anyway. We're not going to be talking about that in the course. I just thought it was cool to show you a picture of the wind tunnel testing from the Burj Khalifa, which is currently the tallest structure in the world. So when we're using the static procedure, if our structure is not dynamically sensitive, we come down here and say, okay, yes, we can use the static procedure. Our static procedure tells us that the pressure on the face of a structure is going to be proportional to an importance factor. We talked about that for snow, and in fact, it's going to be very similar for wind. A reference velocity pressure, right, is going to be a Q value that is velocity based, right? I don't know really why they call it velocity pressure, but it's a value that is going to be calculated based on the velocity that's typical for the wind at the site squared. We're going to have an exposure factor, a topographic factor, a gust factor, and this pressure, I don't know why they call it coefficient, but pressure factor is something that you can use. And we'll unpack what each of these terms means. Importance factor is almost exactly the same as for snow. In fact, for the ultimate limit states, it is the same. For serviceability limit states, we'll come and talk about what these importance factors mean later on. What we're calculating today is the pressures using the ultimate limit states values for importance, because we're trying to quantify how strong the structure needs to be to prevent collapse and have a safe structure. Okay, so everywhere from 0.8 to 1.25, and typically in our class we're going to be dealing with an importance factor of 1, but you may be told it's an importance factor of higher post-disaster. We talked a little bit about what that meant recently. Next, we've got this Q value. And what Q value is a wind velocity pressure, and it's based on the mean hourly wind velocity that's measured at 10 meters above the ground. Okay, this is, I always forget what this is called, anemometer, I believe, anemometer. It measures wind speed and direction. There's these little cups here, and as the wind blows, the cups spin around, and how fast the cups spin around is proportional to the wind velocity, and we get direction. So there's weather stations everywhere. They're typically at airports because there's not a lot of stuff around airports, because if there's stuff around airports, airplanes tend to hit them. So a lot of these are at airports. You might see some next to highways that have wide open space. Basically, they've got these instruments all over the country, and the height of those cups above the ground is pretty consistent at 10 meters. Okay, so the velocity that we're using, V, for wind speed is always going to be a mean hourly velocity that's measured this 10 meters above the ground. We just saw on the previous slide that the Q value, or the effective pressure acting on the face from the wind slowing down, is basically 0.5 times the air density times the velocity squared. Okay, we don't actually use the velocity, we don't use the air density. What the building code has done is they said, okay, we know what the wind speed is, we're going to assume a certain conservative value for the density of the air, and we're going to plot these values in the building code table. We saw this in lecture 6 the other day. We looked up the snow load values from this table to calculate the uniform snow load on the flat roof in lecture on Monday. And if we're looking at Fredericton, for example, we're going to see that if we come over to the 1 in 50 year mean hourly wind pressure, we see we get a value of 0.38 kilopascals. There's also 1 in 10 year here. We don't actually use that. And in fact, what we often use is this importance factor of 0.75 instead. When we determine whether or not a structure is serviceable for wind, we're actually effectively checking it against 1 in 10 year wind speeds. And the 1 in 10 year wind speeds tend to be about 75% of the 1 in 50 year wind speeds. So in this course, we're not using this 1 in 10 year column. We're only using the 1 in 50 year column. And if we're going to check serviceability later, we'll use a factor of 0.75 on those values. Next, we have an exposure factor. The exposure factor accounts for how exposed the structure is to wind. And I think that's pretty straightforward. Quite similar to the wind exposure factor for snow loads that we talked about on Monday, but not the same. The higher a structure is above the ground, the more exposed it is to wind, right? There's a drag. The general rough terrain down here tends to slow the wind down. As you get higher, you get further away from that rougher terrain, and so the building becomes more exposed to higher velocities of wind. And if it's wide open, there's no big trees, there are no tall structures, there are no big hills, and if you're not in a fortified city, then you're in open terrain. And basically that means you calculate an exposure factor that tends to be a little bit higher. And the other thing you're going to see here is it's all with respect to a value of 10. And that seems weird, the height that we're at, right? This is the height above the base. Okay, so this really should be Z over 10 technically, but height above the ground is anywhere from 0 to the height of the structure. It's not necessarily H, though we will tend to use H for this calculation. Why is it with respect to 10? That's kind of weird, H over 10. Did we talk about something already that might be important for where that value comes from? Well, it's all going to be relative to the height of 10 meters. Right, that we measure wind speed at. Okay, so the wind speed is measured at 10 meters above the ground. And in open terrain, we get measurements consistently in 10 meters above the ground. If it's at 10 meters, then we'll get a value of 1, right? 10 over 10 to the 0.2, 1 to the power of anything is 1. And so at 10 meters, the velocity is the velocity. At less than 10 meters, it's a little bit less. Higher than 10 meters, it's a little bit more. And so we use this equation to calculate what we expect the pressure to be above or below that reference height of 10 meters. Technically, we can use Z in this equation, and that's what's shown here in this little figure. It can't be less than 0.9, so it might be 0.9 down here, maybe 1.3 at the height of the roof. But this little bit down here is really not going to be consequential in terms of the total lateral force, right? The total lateral force is this pressure plus this pressure. And if we just emit a little bit of this or add on this extra little bit to make the pressure uniform on that face, we're really not adding a whole lot of force there in terms of the net lateral force, and we're adding even less bending moment. Okay, so it's slightly conservative for us to just say, hey, I'm going to make this non-uniform pressure uniform, because that simplifies the structural analysis. I've got a uniform height. I know what my tributary heights are for the floors, and I can do my analysis this way. Okay, so this is a simplification, and it's conservative to do so. All right, so a conservative simplification for us to just take the uniform pressure with CE calculated using height H. We're also going to have exposure factors for the leeward side. And what we do here is we just use the exposure for H over 2. This is just the building code folks kind of putting their hands up and saying it's turbulent. I don't know how to do turbulent flow, but we're just going to say, well, on average, the suction tends to be about the same over the height, and we'll use the height of the structure divided by 2. If we're calculating exposure for the roof, of course, we're going to use the exposure factor for the height of the structure. Okay, sidewalls here, they're not super important for what we're going to be talking about in this course. What we see is they're equal and opposite anyway, and so there's no net lateral action of our structure from wind on these sidewalls. Okay, does anyone have any questions about this velocity pressure, where you can find it, or the exposure factor, and why we use these calculations to figure out what the exposure to wind might be? Yep.
So in the end, after we calculate all of these, do we put them together?
We'll see. Okay, we'll get there. Next, we've got a topographic factor. And in CE 3063, we're just going to take this as 1. It looks kind of complicated. It's like all these weird, e to the power of stuff, all these crazy coefficients. The pictures make it look easy, but it's actually pretty difficult if you try and analyze what the topography around the structure is going to look like. You might say, well, this building's on the top of a very smooth hill, right? Fredericton is basically one great big hill. If the wind was blowing across it, the pressure of wind on the mall at the top of the hill might be more than the pressure on the building of Head Hall at the base of the hill. That's basically because, again, it's like the area is getting smaller. And so if the wind has this much height to flow through, roughly, and that goes down to this height, then we're going to get a speed up of that wind, and it depends on whether or not there's also a hill on the other side. You need to know that this exists, but in this course, we're just going to take that value as being equal to 1. Next, we have a gust factor. Anyone who's been out in a windstorm knows that, you kind of have the wind's blowing at you, and then all of a sudden, right, you get blown backward by a big gust of wind. Gusts every once in a while will occur. They tend to result in wind speeds that are higher than the mean hourly wind speed. If you go to the weathernetwork.com, the app sucks anyway. I never use Weather Network anymore, but you used to be able to use it, and it was a nice system to use. What they're going to be giving you is actually 2 numbers. They're going to tell you what the mean hourly wind speed is expected to be and the direction of the wind. So they might say, 10 kilometers per hour wind speeds that day, gusts up to 15 kilometers an hour. Okay, so buildings, just like you, feel gusts. It means the velocity is going to be higher. It means the pressure is going to be higher. If you look at all these different values, the ratio is something like 1.5. But again, the velocity tends to be proportional to velocity squared. And so what that means is that the net effect of a gust is 1.5 squared or so, which might be 2.25. Okay, of course, that's not the value you use. They're going to be different depending on the relative velocity of the gust to the mean hourly wind speed. But for buildings, if we're looking at designing braces and brace frames, for example, we're going to be using a gust factor of 2. But if we're designing very localized things like windows, you might not know, but windows are actually usually pressure tested, especially in areas of high hurricane or tornado action, and they have to be able to resist and stay in the wall for a certain velocity. For local checks and local elements, we use 2.5, but for the building overall, we use 2. That might seem weird, and it certainly when you see it the first time, it seems weird. You say, well, why don't I just use 2.5 for the building overall? Why would we use a smaller value for the full structure compared to what we might use for a small localized part of the structure? Well, I might go back very quickly to this picture. The wind, we assume, is more or less uniform, but really as the wind blows, the pressure might be higher up here at a certain instance than it is over here. And then in another instance, it might be higher, down here than it is to the right. So from time to time, the wind at a specific location of the structure is going to be more significant than elsewhere. And so locally, there's going to be a larger effect. But if we take the overall lateral effect of that pressure distribution, it's not 2.5 times, right? Locally, the wind's going to be faster than it is other places of the structure. We say it's not correlated. The pressure at all locations of the structure is not highly correlated. It's not uniform. And so some areas will have higher wind than others, and the net lateral effect is not as significant as the effect locally on certain elements. We're not going to be talking about cladding or local structural members in our course, so we're going to be using a gust factor of 2 for these calculations. Finally, we have this pressure coefficient, and what I want you to think about for pressure coefficient is aerodynamic. How aerodynamic is the structure that we're dealing with? Shorter structures are more aerodynamic than taller structures. And so what we're going to see is a lot of this is going to be based on a height to width ratio. And if we go back here to our exposure factor, for wind in this direction, we're going to be using the width of the building that is along wind or parallel to the direction of wind. And h here is equal to the same little h. Okay, so it's a ratio of the height of the structure to the width in the along wind direction. And so the higher the h over d ratio, the more the wind is going to affect our structure. Okay, so on the windward face, the value is going to be at least 0.6. We can't use anything smaller than that. The higher h over d gets, the closer we get to 0.8, but we don't need to exceed 0.8 as a factor on the windward face. Okay, so we need to calculate the h over d ratio to do that calculation. On the leeward face, we have negative values, okay, between 0.3 and 0.5, again, depending on this h over d ratio. Negative does not mean opposite direction. Negative means away from the face the wind is acting on. Okay, so negative is going to be a suction pressure. Positive is going to be a pushing pressure. So we don't say plus positive value plus negative value is smaller value. We subtract the negative value. Okay, so it's going to be absolute value of positive pressure plus absolute value of negative pressure gives us the total effect on our structure. Okay, so be careful with that in your wind load calculations. Sidewalls, different value, not super important for us. For the design of framing, from time to time, we might have an uplifting pressure, right? The wind's going to pull up on the roof framing. It's not going to be significant for the most part, but in the lecture example, I've extended it to include the uplift on the roof framing. But for the most part, this is not a major focus of this class, okay? Not a major focus in CE 3063. Oops. Does anyone have any questions about this topographic factor? You shouldn't, because it's always going to be 1 for the purposes of our course. The gust factor, you really shouldn't. It's always going to be 2 for the purposes of this course. Or the pressure coefficient, which tends to be a bit more involved to calculate for different structures. The CG factor, right? So this is always going to be 2. In this class, we're always going to take this as 1, CE, you need to calculate, and CP, need to calculate. Okay, cool? Good. One thing that's important and tends to be confusing, more often than not in this course, we're going to be calculating pressures on the windward and leeward faces. They're going to be more or less adding together in terms of the total net effect on the structure. And if you were to consider how much force is at each floor level, we did that exercise in lecture 4 when we said, okay, for pressure on the south face, what's the total force acting on the floor? We need to calculate the total force that's acting on the floor to account for something that's called partial loading. And partial loading can result in twisting effects acting on our structure. And we also use it to account for the fact that wind might be blowing in a direction that is not perpendicular or parallel to the structure. And so if we're looking at wind loading from a different direction that's not just perpendicular to the structure in either of the two major directions, we need to consider a case where we have 75% of the wind acting in one direction, 75% of the wind acting in the other. That shouldn't be super important for the structures in our course, because if we think about which braced frames are taking which forces, this 75% is going to load these braced frames, and this 75% is going to load these braced frames. There's not a significant interaction between the two, but if you had a column that was in a braced frame, and for example, the braced frame was maybe down here and down here, you're going to get load on that braced frame and on that braced frame, and on that column, you might get a little bit more force than you would from just considering the full loading in one of the primary directions. You're not going to need to do this in this class, but you need to know that you have to do that in practice. What some of you will need to consider is eccentric loading from partial loading. What this represents is more or less something like there's a little bit less pressure over here, but there's a little bit more pressure over here. Wind tends to result in wake buffeting and vortex shedding, which means that we're going to get some twisting of the floor back and forth as the wind goes by. If your braced frames are on the outside face, this is not going to be very important for you, because 75% of the load shifted at 15% of the plan dimension is going to result in more force here compared to this side, but this force here is still going to be less than the force on that braced frame from the full loading direction. However, if your braced frames are closer together, some of you have floor plans with bracing that is not at the outside faces, it's closer together within the structure, then that 75% of the load might result in a load that's quite a bit higher on one of those braced frames than the other. Okay, so in class, you need to consider the full loading. You need to consider it both directions. Technically, because our building is symmetric, this way is equal to that way, and left-right is going to be equal to right-left. It just means tension, compression changes for some of those members. And you need to consider this partial eccentric loading here, because if your braced frames are spaced too close together, that's going to result in more load on those braced frames because they're closer to the center of the structure. Okay, does anyone have any questions about this? These top two here being particularly important for you on your building design projects. It's just statics, right? Simple beam's different. My simple beam here looks something like this. Pin, roller, load, compared to something over here where I might have pin, roller, load, right? Statics are different depending on where your brace frames are. That determines what your reaction forces are going to be. You just have a different statics problem to solve. This might result in a larger force there than that one would. Any questions about that concept? Okay. I don't want to talk too much about internal wind pressure. It's not going to be particularly important for you on your design project, but you need to know that it exists. For the most part, we have very similar factors, except they might be slightly different depending on the nature of how exposed your structure is to having wind get into the building. And what I mean by that is a structure like this might have some windows. Wind can blow in the window. What do you think is going to happen if wind blows into the window? What's going to be the effect on the structure? Inside pressure. Anyone blow up a balloon before? Expands, right? So the building's going to want to poof up. And so from time to time, you're going to need to consider that, especially on roof framing or on cladding components. Where it's really important is stuff like garages that are going to remain open during large storms. You've got a great big garage door with nothing else in there. You get a really big windstorm. And it's just going to basically blow your building outwards. And it's going to be very important for you to consider that. For the most part, what that means is you get more outward action on the walls, side walls in particular, and perhaps on the leeward wall. But in terms of the total net action on the structure, this pressure is going to self-equilibrate with this one. This one's going to be in equilibrium with that one. And so the internal pressure doesn't result in any additional force sideways on your structure, which means there's no significant additional lateral force. It might mean that your joists and girders experience some uplift. And so if you've got a big opening, there's going to be wind pushing it up. There's going to be wind pulling it up. And so for really big storage structures where you have large openings like doors that might remain open, you need to consider this, but it's not going to be important, not important in CE 3063. Now, very similar to snow loads the other day, take 30 seconds or so, maybe a minute, maybe two. I want you to figure out what the pressure at the top of the windward face of a 10-meter building might be for a normal importance structure in Fredericton using a CP value of 1. Okay, so we need to be looking at the equation here for wind load. Oh, do I have the slide there for somebody? Some of you might already see it, but so we need to be using this equation here. Normal importance tells us something about what I should be. There's a value, or Fredericton tells us what Q should be. Top of a 10 meters tall structure tells you something about what CE should be. CT and CG should be taken as certain values, and basically I say to take CP as 1. Okay, so take a second to go through that calculation, see if you can get familiar with using that equation for wind pressure, and we'll come back and talk about that here in a second. Okay, so those of you who have trucked on through the question are converging on what I'm pretty sure I remember being the correct answer here, 0.76 kPa. Those of you who are still working on it, that's fine. I do want to do a brief example here, so I want to make sure I'm not rushing too much, though I might need 5 to 7 minutes to do that. Basically, again, putting together the pieces of this puzzle here, we've got a building in Fredericton. That means we should be going to the table and using this value of 0.38 kPa for Q. And normal importance implies we should be using an importance factor of 1. Gust factor is 2. CT for this course is 1. It might just be on flat terrain. And I'm telling you here to take CP of 1. The other piece of information here is it's on the windward face of a 10-meter building, which means the exposure factor, if it's 10 meters tall, 10 over 10 is 1 to the power of 0.2 is 1. And so basically, we can calculate the pressure for that case